Welcome to the sixth lecture of the NITheCS SATACS course in category theory. The last lecture we looked at some of the most fundamental concepts, that of addition and of multiplication of objects in a category. They're usually called product and co-product. But I really like to use the, and not just I, many people prefer to use sum for co-product or addition, and even call product multiplication. And the reason for this is that, well, especially for me, the reason for that is that I really like to see these operations on objects in a category as abstractions of the usual arithmetic operations on natural numbers. And indeed, we saw last time that if we take the category of sets, and we take the product of two objects there, so this will be a product of two sets, the Cartesian product. As we know, well, its number of elements is exactly the product of the number of elements in each set. And the same is true, a similar principle holds for co-product or sum. The number of elements there is the sum of the number of elements in each set. Of course, these sets need to be finite in order for this to make sense, but also these formulas also work for infinite sets where then the addition here and multiplication are operations on cardinal numbers rather than natural numbers. So these laws suggest to us that we can think of Cartesian product of sets as a kind of insight to multiplication of numbers, and the same for co-product, which is disjoint union of sets. We can think of it as a almost more fundamental operation than the operation of addition itself. And this is actually not too surprising, because when we explain, especially when we explain addition to a very young human being, when they learn it for the first time, we usually use sets to demonstrate what addition does. We might have 3 sticks on one side and 4 sticks on the other side, and then we will put them together and we'll say, okay, now let's count how many of them we have in total. So you see, we are forming the disjoint union of sets in order to explain addition of numbers. And that kind of confirms, I think, that indeed disjoint union of sets is more fundamental operation than addition of numbers. And categorical sum is a direct generalization of disjoint union, because that's a concept in an arbitrary category, where in the category of sets it becomes exactly disjoint union. And something similar can be said also about multiplication. So viewing these operations as a sort of generalized arithmetic, sometimes I like to call it higher arithmetic, we might want to ask ourselves, do we have laws similar to the usual arithmetic laws? Do they transfer to more general categories? Okay, so let's write down one of the most basic laws that we know is true for usual arithmetic, and let's see if we can do something about it in the general case. Any suggestions? What would you consider as one of the most basic laws of natural number arithmetic?
By law, do you mean an operation, binary operation like addition, multiplication?
So there is a difference between an operation, which is a structure, it creates things out of existing things, and between a property that such a process of creation can have. When we say law, we mean not the structure, but the properties, the axioms that the structure will satisfy.
Okay.
So what is basic fact about, for instance, addition that comes to your mind? Well, let me rather say here, instead of transfer, let me say generalize. So what is an example of some very simple and basic principle um, about addition?
Nothing is coming to mind at the moment.
I think maybe I'm not phrasing the question in a clear way. Fosco, what would be for you one of the most basic? Sorry for asking you a trivial question, but
no problem. I'm happy to answer. Try to answer. Well, I guess the distributivity of multiplication over sums is a good starting point.
all right. So in arithmetic, we have this rule: a times b. Thank you very much, Fosco. A times b plus c equals a times b plus a times c. And this is true for all natural numbers a, b, and c, right? We might now ask a question whether this is true or not in every category where the sum and the product of these objects are defined. It turns out that the answer is no in this case. This turns out to be a rather strong property. That's not always true. And maybe one of the most straightforward examples would be a lattice viewed as a category, where this law would force the lattice to be distributive, and not every lattice is distributive. Here is an example of a non-distributive lattice. So I'm going to, since we didn't talk about lattices before, I'm going to just talk about them as categories. So here is an example of a category where this law fails. I've got these objects in the category, and the arrows are shown as shown on the diagram. These are not all of the arrows. There are some more. For instance, the necessary ones in order to have composition are also there, but I'm not drawing on the picture. For instance, there's also an arrow going this way. And also there are the identity arrows, which are also not drawing. So I've just drew some minimal number of arrows, where all the others can be generated from these by composition. And any two composites are always equal. For instance, any two comparable composites. For instance, this arrow here that's composite of these two, we will think of it as being the same arrow as this composite. This is a special kind of a category. It's a category where from any object to any other object, there's always at most one arrow. Now, it is not difficult to show that in this category, products and sums of objects do exist. For instance, if we take these two objects, their product will be the largest thing that's below both of them. So below means that it has arrows pointing to both of them. And so that will be this bottom thing here. Whereas sum would be the other way around. So sum would be something there. So the smallest one that's above both of them. We could actually write down a kind of multiplication or product and sum tables for these. So let's call these things something. Let's call this bottom thing, maybe I'll use a symbol that logicians like to use, and this is the top element. And let's call these capital A, B, and C. And we can then set up a table for product to show all the products here and all the sums. It will be a large table, right? 5. I need 5 rows and 5 columns. 1, 2, 3, 4, and 5. So we got these 2 special elements, this one and that one. And then we also have ABC. There is actually a simpler way of thinking about this, which is to think of these as specific numbers. So they will be co-prime numbers, the A, B, and the C. Let's say 2, 3, and 5. And we think of the bottom one as number 1. And we think of the top one as the lowest common multiple of 2, 3, and 5, which I believe is 30, if I'm not mistaken. And if I think of it like that, then I can free myself from setting up the table, because then I can describe these operations more easily. So x times y in this case will be GCD of x and y, and x plus y will be LCM of x and y. It turns out that, in fact, even if we take a bigger category, and these arrows now, I think it should be indicative of what these arrows represent. So an arrow in this category, an arrow from x to y, represents, so it exists if and only if y is divisible by x. So when an arrow exists from x to y, it's always unique. There can't be more than one arrow. When it exists, it's always one, and it exists if and only if the second of these two numbers is divisible by the first one. It turns out this indeed is a category, and moreover, it turns out that so it's a category even if I take all the numbers. I don't have to just take 1, 2, 3, 5, and 30. I can take all the natural numbers. So this would be a category with objects being natural numbers and morphisms being defined this way. And it turns out that in this category, product will be GCD and sum will be LCM. And then we can now confirm that this rule of distributivity will fail here. And maybe after we confirm that, we will go back to this category and analyze why this is true in that category. So let's substitute some values for A, B, and C to make this fail. And I think my picture should be suggestive that we're going to take A equals 2, B equals 3, and C equals 5. So what is, so I need to now replace product with GCD and sum with LCM, right? So I'll have GCD of A and something called B plus C. So A is 2 here, And B plus C is LCM, so I'll have LCM here of 3 and 5. So GCD of LCM of 3 and 5 is the question is whether it's equal to or not to LCM of GCD of 2 and 3 and GCD of 2 and 5, right? So this left side is the A cross B plus C thing, and the right side is the A cross B plus A cross C thing. Is that clear, Okotisa, for you?
Yes,
that,
it is.
Yeah, okay, great. And what about Makawe? I'm not sure. Here's a mic. Do you have a microphone? I'm not sure I can see whether you've got a microphone or not. But feel free to say if something is not clear, Makawe. Okay, so let's calculate this. This thing here is GCD of 2 and what is LCM of 3 and 5? It's 30, right? What is GCD of 2 and 30? It's 2. On the other hand here, GCD of 2 and 3 is 1, of 2 and 5 is also 1. And what is LCM of 1 and 1? It's 1. And unfortunately, 1, or maybe fortunately, 1 doesn't equal to 2. Hence, in this
I
category,
think the LCM of 3 and 5 is 15, not 30.
yes, of course, thank you. Well, I was in my mind still working in the smaller category where it would have been 13, but 30, but you're right.
Certainly, yeah, but it
yeah.
might be confusing to hear that.
No, absolutely no, because I did say that we switch to the bigger category. So, and these formulas only work if we do switch to the bigger category. So this will be 15 here, which breaks the hypothesis, right? Because now it's still now it's no longer equal to 2, it's equal to 1. And so the formula holds. So I really want to choose my numbers in such a way that that it might, yeah, this might not be possible. Okay, now let's think about this. Is it possible to choose our numbers in such a way that thing here will be LCM for both this pair and, sorry, that this thing will be an LCM of this pair. That's all I need. But at the same time, I want 2 to divide it. But then GCD of both pairs to be 1, of 2, 3, and 2, 5. It's an interesting puzzle. Okay, so what I want is for the argument that I was trying to give, for it to work, what I want is to name 3 numbers so that pairwise their LCMs will be the top, and pairwise their GCDs will be the bottom one. So we just need 3 numbers like that. And if I choose this to be 1, then these have to be coprimes, right? But if they're coprimes, then what I wanted to do might no longer be achievable. Let's solve this puzzle together. I think this is where I have to activate the warning I gave you before the lecture, which was not recorded. But I was very ill for the last few days, and my mind might not be so fresh.
Yeah, so definitely there's no LCM of yeah, for 3 and 5, there's no way you can find a GCD where 2 divides what is it? The LCM
Yeah.
of 3 and 5.
Yeah, I agree. If
So going
what if we
higher,
put something else here? Is it still not possible? For instance, this could be 2 times 3, and this could be 2 times 5. And no, that can't be that, sorry. This has to be 2 times 5. And this will be 2 times 3 times 5, right? The LCM. And I can have 2 times 2 here. But then
they're no longer co-prime, right? The middle one.
yeah, they're no longer coprime. That's true. There is some general knowledge I'm using according to which, if I'm not mistaken, if I'm not misremembering something, we should be able to solve this puzzle. And the general knowledge, let me at least say it, is that so this divisibility lattice of numbers corresponds to the subgroup lattice of the group of integers. And that subgroup lattice, I don't think is distributive. So that's from my memory. Okay, well, let's give it one more try, and then we can postpone it for our own independent thinking. Is there anything else I could do here? Yeah, I think. Yeah, the thing is that whatever number we put here, we could always later divide every term by that number, right? And get another picture that should be similar. So maybe if it's not possible to do it for 1, then it won't be possible to do it for any other number as well. If I've got a number, let's say I've got a number x here. If this is divisible by x, so it's something like x times y, right? And the other number is something like x times z, where y and z will have to be coprime in order for x to be their GCD. And similarly, I need to have x times t here in order for the GCD of these two to be x. And so t, y, and z will have to be all coprime. But now, when we try to look at LCM will, because y and z are coprime, LCM of x of these two terms will be x times y times z, right? And now we are forcing this to divide that, but we said that T and Y are coprime, T and Z are coprime, and so T won't be able to divide Y times Z. So it's not possible, actually. All right, I'll have to revisit my memory and understand what I misremembered wrong. Sorry about that. So let me retract this interpretation with numbers. And thank you, Bosco, for picking this up. Otherwise, it would have stayed on, probably. It would have been an embarrassment. Okay. So let us not think about these as numbers, but I still want to give it some concrete interpretation, so maybe it's easier to think of those things. Let me try them with sets. So the bottom one will be the empty set, and here we will have three sets: singleton of X, singleton of Y, and okay, let's call them 1, 2, 3. Singleton of 1, singleton of 2, and singleton of 3. And here, let's take the set 1, 2, 3. So we are only considering these sets, not any other set. And the arrow this time represents that one set is a subset of the other. So an arrow from X to Y here, in this modified example, represents that X is a subset of Y. The picture kind of suggests what will be sum and product here. The sum of these two things, as we remember from the previous lecture, must be something with arrows going into it, right? And so there is only one thing that has that property, that there are arrows going into that. And it is not difficult to see it will actually have the universal property as well, because when we have this as a sum and we have something else like that, there must be this unique arrow. So for these two, if I want to find another pair like that other pair will have to be, again, the same one. And so the unique arrow will be the identity arrow. So sum of each of these two, here, these two and those two is always that. So it's not quite union, right? But because we threw away some sets, we only kept these specific sets, then it becomes, you basically can think of it like this: take the union and then take something, a set that's closest to it above it, that's inside the selected sets, which is then this. Whereas the product is kind of, in this case, it's exactly an intersection. So the product of these two will be empty set and so on. And then if I call these A, B, and C, A cross B plus C will equal to A cross, and let this be called D. It will equal A cross D, which is A, because A is below D. But on the other hand, A cross B plus A cross C, what will it be? So A cross B will be empty set, so it will be empty set plus empty set, and that gives us the empty set. And we see that these two things are not equal to each other. So distributivity does not always work. But maybe before coming back to the original question we asked, maybe it is worthwhile to expand on these kinds of examples we were trying to build here. How do we build examples like this of a category? I want to check if we have already looked at a topic like that. Have we already looked at viewing partially ordered sets as categories? Seems like we haven't, right? Maybe very initially, very little bit, but not too formally at least. Okay, so let's look at that then. Before answering the question above, it would be good to have a sort of test ground for categorical arithmetic, by which I mean arithmetic inside general categories. Different from the category of sets. And we will now develop an entire class of examples of categories where additional multiplication will become something very meaningful, something very different from additional multiplication of numbers. But it will be good for us to have those examples as well, so that we can then be able to better judge what can be generalized to general categories and what can't be. Obviously, things that are false in that new test ground can't be generalized, because if it was true in general, it would have also applied to all the special cases, right? Here's the definition. A preorder is a category where for any two objects, x and y, and let me say for not any, but for every, to make the quantifier I'm using here more clear. For every two objects x and y, there is at, or actually, okay, let me phrase it like this. There is always at most one morphism going from x to y. It is exactly of the kind of category that I was trying to illustrate above. It is a very strange category from the perspective of the category of sets, right? Because when you have two sets, x and y, usually you've got many functions from x to y. As soon as y has more than one element, there are many ways, and x is non-empty, there are many ways to map elements of x into elements of y. So it's a very different scenario to the category of sets, where there is always at most one morphism. Once I fix two objects in a given direction, there is always at most one morphism. Interestingly, something happens in this case to associativity and the identity laws. They kind of trivialize. We can view such category in terms of the set of objects and the binary relation defined like this. Let's write x less or equal to y when there exists a morphism from x to y. So there exists morphism from x to y. Since there is always at most one morphism, knowing when it exists basically gives the information on what the morphisms are. It doesn't tell us exactly what the morphisms are, but it tells us what they are, let's say, up to bijection. If I think of this binary relation as a kind of ordering relation, and that's where the term preorder comes from, we can express the axioms of such a category in the language of this relation as follows. Then composition the operation of composition and this is an example of Quatisa where what previously was a structure now becomes a law, a property. Then the operation of composition reduces to the law that if x is less or equal to y and y is less or equal to z, then x must be less or equal to z. So what do I mean by saying that it reduces to a law? A composition must choose, right? For every pair f and g, it must choose a third arrow, which is g composed with f. Right? That's what composition does. It chooses an arrow. So it's not just an implication in general. It's a choice. It's a mapping. But when in our category there is always at most one arrow in a given direction, the choice becomes uniquely determined, right? If I have to define composition of these two morphisms, and I know that there is always at most one morphism from x to z, then I have to define the composite to be that unique morphism when it exists, but I actually even have to require that it exists as well, right? And the requirement of the existence is this part, and exactly how to define it doesn't matter because there is only one choice, so it will have to be defined in a unique way. Does that make sense, Quatisa? I'm asking you because I think it's a very new concept to somebody who hasn't done master studies yet.
Yeah, I think it makes sense. I think it makes sense. I'll still think about that. So I think it's an axiom just because it's uniquely determined.
Yeah. So we don't have to.
Okay.
Yeah, we don't have to make choices anymore because there is only one. If there is an arrow available in this direction, it will be only one of them. So there are no choices to make anymore in terms of defining how the composition works.
Yeah, so that's fine.
So the process of choosing composites now becomes just the fact of possibility of choosing them because the specific way of choosing them is uniquely determined. So it becomes a property or a law of the less or equal relation. And similarly, the existence of identity maps, the existence of identity morphisms becomes the law that x must always be less or equal to x, right? This is true for every x. So remember that identity morphisms ask for there to be morphism for every object X. There must be morphism from X to X, and existence of such a thing is expressed by this. Of course, this thing needs to satisfy something more than just that. It needs to satisfy that identity composed with anything on one side equals back that thing. So it needs to satisfy that these two things are equal. And it also needs to satisfy that these composite f with identity of y, let's say, is equal to the same f here. But in our case, these equalities will be true automatically. Once I have at most one morphism between every two objects, and once I know that there is always something from X to X, expressed by writing that X is less than or equal to X, then these two properties will automatically hold. Would anyone like to say why they will automatically hold? Why will the composite F and identity equal F? And why will composite of identity and F equal F? In our scenario where we're considering a situation where there's always at most one morphism between every two objects. So maybe I'll draw the composite and it'll be maybe easier to answer the question. So the composite of F and identity must be an arrow from X to Y, and the composite of identity and F must also be an arrow from X to Y. Does that make it clearer?
So is every morphism an isomorphism in this category?
Sorry about that. No, not necessarily. Not every morphism is an isomorphism, but we have this principle that for every two objects, X and Y, there is always at most one morphism from X to Y. So what happens if we apply that principle to this X and Y here? Doesn't that principle tell us that there must be at most one morphism from this X to that Y?
Yes, yeah, that's fine, yeah.
And so there can't be two of them, right? So if these are morphisms, they're both morphisms from X to Y, so they must be equal because there is at most one such, right? Does that make sense?
Yeah.
Mm-hmm. The laws of identity and even associativity, and I'm going to draw a picture for that as well, hold trivially. So why does associativity also hold trivially? So if I've got three of them, H, G, and F, associativity tells me that when I consider this composite, G composed with F, and then compose that with H composed with G composed with F, associativity tells me that that thing should be the same as first composing these two, and then composing that with F. Right? So associativity is a law that forces this arrow to equal this arrow every time they're built out of three things like that. Now, in our setup, when between every x and y, there is at most one morphism between them, why will this be trivially true? Why will this arrow be equal to that arrow?
Is it just because of the definition of the morphism?
So we know that there must be at most one morphism from x to t, right?
Mm.
And so if there are two of them, they will have to be the same. You agree with that?
Yeah, yeah.
So they're equal. So the whole concept of a category simplifies a lot when in a category, for every two objects x and y, there is always at most one morphism from x to y. It simplifies a lot, and it basically reduces to having a binary relation on a set, which is transitive and reflexive. This is called transitivity for a binary relation. To have a property like that is called transitivity, and this is called reflexivity. So we can now write, so a preorder is, and I'll say the same as in quotation marks, because it's intuitively it's the same thing. Structurally, as a data of information is not quite the same thing, because these compositions still have to be, even though they're uniquely determined, they have to be still listed in order for us to have a category. But because they're uniquely determined, we don't care to list them anymore. So there is some change of data a little bit. But essentially, conceptually, and in the essence of these concepts, they're the same. So a preorder is the same as a set, and this would be the set of objects equipped with a reflexive and transitive binary relation. In other words, a pair x less or equal, where the two properties hold for every x, y, and z in, let me use capital letters because there were objects before. For every x, y, and z there, we've got that x is less or equal to y, and y is less or equal to z, implies x is less or equal to z. And at the same time, for every x, we've got that x is less or equal to x. What are examples of such kind of categories? I just have to name pairs like these, right? Pair of a set and a binary relation that satisfies these two laws. Would anyone like to suggest your favorite examples of such a structure? We'll make a list of a few of them.
The set of natural numbers.
That's a good idea. Let's take the set of natural numbers. What would you take as your binary relation?
You have the less or equal to.
The usual less or equal relation. That's a fantastic example. We know that these laws hold for it, right?
Mm.
So it's all good. Another one is the divisibility one I was attempting to talk about before. So x divides y. We say x divides y when y is divisible by x. In other words, there exists a z, a natural number as well, such that x times z equals y. So that's what it means for y to be divisible by x, right? A third example is take any set x and take its power set. So the set of all subsets of a given set x, and take the relation to be subset inclusion. That's also an example of a preorder. We could also reverse these relations. We could take the same thing, but now change the direction of the relation. We could do this in all the other cases as well. So there are many examples. Now let's see what will happen to the concepts of plus and product. In other words, what will happen to our arithmetic in the realm of the preorder? We already know that things simplify in a preorder, right? Like if we look here, we saw that the identity law of a category and the associativity of composition law of a category, they come out for free. They hold for free just because of that absence, let me say, absence of morphisms. We've got very few morphisms in a preorder, only at most one for every two objects. So that lack of morphisms makes associativity law and identity law hold for free. So maybe the definitions of addition and multiplication, maybe they will also simplify in a preorder, and we will now see that indeed they do. So now let's revisit the definition of addition and multiplication in a category, but now we apply this definition in the case of a preorder, and we will examine what they will be for the examples of preorder we just gave. Let me remind you that if I have two objects in the category, their sum is a third object together with chosen morphisms. We were calling it iota 1 and iota 2. And the definition says that this will be a sum when for every object C and for every two morphisms, F and G, there will exist a unique morphism H, such that H composed with iota 1 equal F, and H composed with iota 2 equal G. And let's try simplifying this, seeing what comes out for free when we are in a preorder. To give you a hint of what I'm trying to, what I will do next is let me draw those composites. H composed with iota 1 and H composed with iota 2.
Should it be iota 2 composed with H? Or,
I think it is correct because we always write, so it's like with functions. So when I say f, when I say u composed with v of x, it means u applied to v of x, right? So it's always the right-hand side one, which is the arrow that is applied first. And so here,
okay, yeah.
We are first taking the iota 2 root and then following it with the h root. And so I think it's correct. Thanks.
Okay.
We're in a preorder. What happens in a preorder? Any two morphisms that have the same domain and the same codomain, that have the same starting point and the same ending point, any such two morphisms are always equal because there is always at most one such, right? So this automatically forces these two equalities to hold because there we go. If I apply the definition of a preorder for x and c, I get this is one morphism from x to c, this is the other one, so they must be equal. So this part holds what's the right word to say here? This can be dropped from the definition in the case of a preorder.
Trivially true.
Yeah. So we don't have to worry about these anymore because, as you said, they trivially hold. Even the uniqueness of H, because there is at most one morphism always, right? So if H exists, it will be exactly one. So also that part drops. Can be dropped too. And then the rest of the definition of sum is expressible purely in terms of the less or equal relation, and the definition says that so sum in a preorder becomes that x plus y is a sum of x and y when I still need existence of these iota 1 and iota 2. So when x is less or equal to x plus y, and also y is less or equal to x plus y, I don't need to say anymore, I don't need to give names to these morphisms anymore because there is always one morphism when it exists in each case. So I can just think of that unique morphism. I don't have to name it anymore. So this part of the definition is just saying that we've got these inequalities. And then I need to say that for every f and g, right? But now f is also unique once I fix a c, right? So basically what I need to say is for every c for which the f and g exist, so in addition to these two, we also have that for any c such that x is less or equal to c, so that's my f, and y is less or equal to c, that's my g. For any such c, now I need to say that exists unique h. Uniqueness I don't need to say, I just need to say that exists h, but existence of h means that x plus y is less than c, right? For any c such that x is less than c and y is less than c, we have that x plus y is also less than c. So what does the definition say? This sum must be an element, an object in the preorder, such that it is bigger or equal to x, it is bigger or equal to y, and if anything else is also bigger or equal to both of them, then that thing will be smaller than that other thing. So it is smallest among all those things that are bigger or equal to both x and y. That's the intuition, right? In other words, x plus y is the smallest among all those that are bigger than both x and y. And I think in this case, after this clarification, I think it becomes quite obvious what will happen here. In this preorder where being bigger means that that number divides the first one, this will be the smallest that is divisible by both x and y, but smallest in this relation. So anything else is divisible by x and y, it must also be divisible by this. Isn't this exactly the GCD? Sorry, LCM, not GCD, LCM of x and y. Let's pause on this a little bit. Do we agree on the fact that this is exactly the LCM?
Yeah, another term would be supremum, right? The least upper bound.
Yeah. Wait, sorry. Yeah, the lowest LCM stands for lowest common multiple, and then another one would be least upper bound. Yeah, so the term least upper bound is a good term for a general preorder, right? Let's write it here. Thanks for that. So x plus y is the least upper bound of x and y. And in this specific case, this least upper bound is the same as lowest common multiple. But what about in a more standard preorder? What will it be here? Any thoughts?
Because we have equality, we can say it's the minimum rather than just, oh, isn't, I mean, that's the maximum, sorry.
Yeah, exactly.
Just supreme.
Exactly, well done. Yeah, exactly. It's the max. It's easy to get mixed up between the two. It's the max of the two because it needs to be smaller than everything else that's bigger than both of them. But this is a linearly ordered set, natural numbers, right? Everything bigger than both will always be bigger, the same as everything bigger than one of them, the one that's maximum, and then that one is the smallest among all such.
Yeah.
Yeah. Okay. Now exactly the dual picture, the opposite picture, happens with multiplication. Oh, before we move to multiplication, let's also look at this example. The power set of a set, and this relation being less or equal relation, what will be there? Not less or equal, sorry. I meant to say the subset relation. So while you're thinking, let me restate the definition. So in this case, so x plus y is a subset. Okay, first of all, I shouldn't say x plus y anymore because I've got the x as my base set here. Maybe I will rename my base set to something else. Let's call it A. So we are now talking about the subsets of a set A. X and Y are both subsets of A. This will be something that contains both X and Y as subsets and is smallest among all of these. So it's a subset of every other subset that contains both X and Y as subsets. You got a suggestion? What do you think it should be? Let's pick an example. Let's say A was the set having 1, 2, 3 in it. And we picked X to be the set having just 1 and 2 in it, maybe, and Y to be the set having, well, you know what? I want something bigger to make it more interesting in a sense. So let's say my A is this. And Y is a set having 2, 3, and 4 in it. Now, what we know about this is that it must contain this subset X, it must contain Y, but also anything that contains both of them must be containing X plus Y as well. What will be X plus Y in this case?
So the union of X
Yeah.
and Y.
Exactly. It will be the union. Yeah, well done. So we get union. And isn't it remarkable that these things, which seem to be very different from each other, I mean, the LCM operation, the max operation, the union operation, and the disjoint union of sets in the category of sets, they're all simply different forms of the same concept of addition of objects in a general category.
Yeah, that's very powerful.
Yeah. And I think it is appreciation of such connections that attracts one to studying category theory. Of course, not everybody appreciates things the same way. People have different tastes. But if this analogy of these constructions and their common generalization through the sum of objects, if that triggers your feelings, it means that you might want to do study some category theory, because the subject of category theory is all about finding such common patterns across different kinds of mathematical structures and extracting unified concepts from those patterns.
Well, yeah, that's definitely what I was attracted to, that power of abstracting within country, abstracting and connecting different ideas into a single idea.
Right, right. Okay, fantastic. Now, a similar story can be told about multiplication. If I go back and I reverse the direction of all the arrows, right? The product can be obtained from sum by reversing directions of arrows, as we saw last lecture. So all these arrows will be now going backwards. But that corresponds to reversing our relation, doesn't it? The pre-order property will still make the dual of this hold automatically. It will just swap the order of composition here and here, and iotas will become pi's. But by uniqueness of those arrows, it will automatically hold. It is the same goes here. This uniqueness part will automatically hold. So everything will be just swapped around and nothing else changes. So it's basically the same as swapping direction of inequality around in this simplified formulation of sum in a pre-order. So let me copy this down and then swap the direction and see what we get there. So now let us look at the concept of product. In a pre-order. So I'm going to erase all the lesser equals and write bigger or equal in their place, because that's the effect of swapping the direction of arrows, right? So this will be bigger or equal to. Maybe I want to use a different color for that. This will be bigger or equal to. This will be bigger or equal to. This will be bigger or equal to, and this will be bigger or equal to as well, and here will be bigger or equal to as well. So what are we getting now? Oh, first of all, also sum needs to be replaced with product. So now, what is this product? It's something that's less than both of the initial two objects, the two starting objects. It's less than both of them. And then if anything else is less than both of them, that product is bigger than that other thing, right? So x cross y is the greatest lower bound, right?
Yes.
And if we revisit the examples, these examples, then after all of this discussion, it should be immediate how we can complete this table of examples for product. So when I put product here, instead of LCM, we will have GCD, greatest common divisor, because it's greatest lower bound. And here, instead of max, we will have min. Maybe I should have written this in yellow as well. And finally, instead of union, we will have, what do you think we will have instead of union?
Yeah, intersection.
That's right, yeah. Sorry. Now that we've clarified this concept of a preorder and the concept of how to think of additional multiplication in a preorder, let's go back to the example that I was giving at the start of the lecture. Let's go back to this preorder. Now we know for sure that it is sufficient to define to describe a preorder in terms of just binary relation. And let me even drop the arrow symbol here, because this is what people working in order theory like to do. They draw these diagrams, they call them Hasse diagrams. Direction of arrow is always going up, so we don't have to draw them. So if I draw a diagram like this, what I mean is a preorder with direction of arrows pointing always upwards. But if they're always upwards, then I can be more efficient and can just not draw those arrows.
Okay.
Sum is lowest upper bound, and product is greatest lower bound, right?
Yeah.
Great. Now let's take ABC. What is A times B plus C? B plus C is smallest upper bound. What is smallest upper bound of B and C? Well, clearly it's D, right? We can see on the picture, it's the smallest node that is bigger than both. Do you agree on that?
Okay. Yeah, yeah.
Between A and D, what is the greatest lower bound between A and D?
Is it A? Yeah. A.
Yeah, when they're comparable, then it becomes min, right?
Yeah, yeah.
So it's A. On the other hand, now let's calculate this one. So what is greatest lower bound of A and B?
So yeah, it will be E. Yes.
That will be E. And the other one will also be E. What is upper bound, smallest upper bound of E and E?
Yeah, E again.
It's E. And E is not equal to A. I think this example becomes now more clear, right?
Yeah, this is, yeah.
Okay, so distributivity does not hold in every category. It holds in the category of sets. So the law of distributivity of numbers, which of course is a very important law, it does hold. But if we switch to some preorders, like this very strange preorder, then the law of distributivity here fails. So it can't be true for every category in general. Yet there are many important categories where it is true. And I think we sort of proved, we might have sort of proved that it is true for the divisibility as well. because there is a theorem in order theory that for your preorder, the one where any two objects have both sum and product. The sum and product, let's say, always exist in a preorder. For that to have distributive law to be true, it is equivalent of not being able to find such a picture inside it, where the LCM of the least upper bound of each of these pairs is D, and for greatest lower bound for each of those pairs is E. If I can't find such a picture, and I should also not be able to find a picture of a different kind, which is of this kind, if these two pictures cannot be found inside my preorder, then it's equivalent for the preorder to be distributive. And we saw that we couldn't find those pictures with divisibility, right? We tried, and we actually gave reasons why we can't find them. So now that it's all coming back to me, it actually turns out that the divisibility lattice of numbers is a distributive. So my initial attempt to give a counterexample with the numbers with divisibility relation would have never worked, because actually it is distributive, and the proof of its distributivity is basically what we already discovered with this small investigation of a failed attempt to produce a picture like this. Okay. So, but not only that, not only in here, but even in these two situations, distributive also holds. Let's look at where does distributivity hold? So it turns out it holds here. It turns out it holds here as well. This is mean and max business. And the reason why it holds there is because, of course, this is a linearly ordered set, right? In the sense that the picture for that would be this. So we've got 0, 1, 2, 3, 4, and so on. And when you have a picture like this, by applying that earlier theorem I told you about, we can definitely not find inside that picture either this picture or the other one, right? Because they require these elements to be non-comparable, and here everything is comparable with each other, any two things. So they don't take, these two don't exist in this line. Sorry?
When you say linear order, you mean a partial order? That's a.
I
is
mean,
that the same thing?
Yeah. So partial order is a preorder with additional axiom of antisymmetry, right? Which says that.
Yeah.
But linear order is even stronger. It means that they're lined up in a chain. So it means that for every x and y, either this is true or the other one. For every x and y, one of them will always be true. That's much stronger than just being a partial order.
Okay.
So there is this geometric way of confirming that this is also going to have distributivity law hold in it, but there is also one can also confirm it by direct case-by-case proof for sorry, just use that formula with mean and max operations, and then you'll see that distributivity holds if you check all the cases of who is greater than whom and so on. And then also, it turns out that even these lattices, I keep calling them lattices. So what is a lattice? A lattice is a partial order where sum of any two objects exist and also product of any two objects exist. So in this case, distributivity still holds. And this is something familiar to us because we know that that x intersected with y union z is equal to x intersected with y union x intersected with z, right?
Yeah, that's pretty
Yeah,
standard.
that's pretty standard indeed. So distributivity law, although it doesn't hold in every category, like in strange categories like this one, it doesn't hold. But this is not the only one. There are many other categories it doesn't hold as well. Although it doesn't hold in every category, it still holds in many, many categories, which is quite fascinating. But this law of numbers, the distributive law of numbers, can be found in other categories as well. And they give some very standard and fundamental facts in other places, like distributivity of meet over join, for instance. Yet, because the law doesn't hold in at least one category, it means that in a general category, we will not be able to prove that it's true. But now, let me take us back to my very first question. I kind of build the rest of the lecture on Fosco's answer to the question. He suggested us to look at distributivity, and that's how we ended up discussing what we discussed. And I'm grateful to him, although he had to leave earlier. Let me go back to the question where I asked, where are we? Do basic laws of arithmetic generalize to abstract categories? Well, we saw that distributivity doesn't quite generalize to completely abstract categories, right? What other basic laws of arithmetic can we write down that perhaps we will be able to generalize them? Would you like to give another try on suggesting how to answer?
I believe associativity is
okay. That's a good one. The following laws of basic arithmetic, or rather the following basic laws of arithmetic do generalize to abstract categories. Associativity, I'm writing with capital letters because I'm thinking of them as objects of a category. But also commutativity. That would also be possible to prove more generally. What is interesting, though, is that we will be able to prove these not quite the same way that we did before, that we could have done before. In other words, we will not quite get equalities there, but instead we will get isomorphisms. Let me move to next area on the board to have more space to continue writing. So they do generalize, but up to isomorphism, let's say. Up to isos. Iso is a nice short form of isomorphism. People often say iso instead of isomorphism. So I'm inserting this additional symbol to represent isomorphism. Now, why is that? Even if you go back to the category of sets, you don't quite get that this disjoint union is exactly equal necessarily to that disjoint union, because when we form disjoint union, we have to duplicate elements to ensure that the sets are not overlapping each other. And the following thing can happen. So if I formally calculate this in the category of sets, if I calculate disjoint union, I will get the following. So every time I take disjoint union, I Cartesian product one with, let's say, number 1 and the other with number 2. And then take their union. So this is a way of ensuring that the elements don't overlap before I take their union, because I want the number of elements to add, right? If they overlap, that will fail. And now let's unpack this as well. So we do something similar inside B plus C. So it will be B cross identity union, not identity, sorry, singleton, C cross 2, and then the whole thing is cross 2. And if I expand it, because product is distributive over union, if I expand it, I get A cross singleton union, B cross singleton, bracket cross another singleton, and then union C cross this, cross that. Whereas on the other side, if I first do disjoint union of A plus B, and then add C to it, I will get A plus B cross 1 union C cross 2. And here inside A plus B, I will have A cross 1 plus B cross 2, and that whole thing is still being crossed with singleton 1. And then we have union C, oh, sorry, this should be union here already. C cross with 2. And here we'll have A cross with 1, and then brackets cross with 1, union B cross 2, cross with 1, and then again union with C cross with 2. And if we compare these expressions, we see that they're not identical sets because, for instance, here, elements of A appear in the form of pairs, A comma 1. Whereas in this set, elements of A appear in the form of pairs, A comma 1, comma 1. Of course, because these coordinates can only be one value, we have a nice bijection between these kinds of things and those kinds of things, but it will only be bijection, it will not be equality. Obviously, this is not equal to that, right? Does that make sense, Okwatisa?
Yeah, there was another terminology which I've heard before. So I don't know who said it. Unique to up to unique isomorphism. So
Yes. So this is
I was not sure what that meant.
yeah. So we are coming to that. So what it means is that, but that isomorphism will also be unique in a certain way. But before we come to uniqueness, let me first finish this. So this is not equal strictly to A plus B plus C, but there is a bijection between them, or an isomorphism. Because in the category of sets, isomorphisms are exactly bijections. So what in arithmetic previously, and this is already sets, right? This is our model for a number arithmetic. When we do number arithmetic, we count elements, and when you count elements in these two sets, because they're bijective, they have the same amount of elements, so their numbers will equal, but the sets themselves will not equal. They will be bijective, and so it kind of illustrates this idea that what before in usual arithmetic was a strict equality, now in this more generalized arithmetic, in general categories, the best we can hope for is to have instead isomorphisms instead of equalities. But we will see that having isomorphism is not so disadvantageous, actually. We can do pretty much everything we could with just having isomorphisms instead of having equalities. Another remark that needs to be made here is that because product is dual to sum, once we establish these laws for sum, just by reversing the directions of arrows, we can establish, and that wouldn't require a separate proof, as I said, it's just by duality. We would have established similar laws for product. And that's another fascinating thing, that we don't have to reprove these laws for product anymore. Once we know them for sums, then we can have them for products as well. Dually, we're going to have these isomorphisms as well. And once again, here it is possible to illustrate that in the category of sets, this is not equality, this is just isomorphism, because A cross B equals the set of all pairs AB, such that A is in A and B is in B, whereas B cross A is a set of all pairs of BA, such that B is in B and A is in A. And as we see, these sets in general are not equal to each other, because here the first component is the one that comes from A, here the second component that is the one that comes from A. The pair AB is not the same as the pair BA. But of course, there is a one-to-one correspondence between them. So just maybe a simpler way to see that the laws become up to isomorphism rather than remaining as equalities. Okay. What we will try now in the rest of this lecture is to prove one of these laws, to get convinced that they indeed hold in general categories. Associativity will require a bit longer time, so to take into account how much time we've got left, we will do just the commutativity. So let's formulate this as a theorem. But before I do that, are there any questions you might want to ask Okotisa?
No, I think I do want to see how we're going to prove the commutativity here.
Okay, fantastic. In every category, given two objects, X and Y, if X cross Y, Y1, Y2, and so this is one product, and now I want the other swapped around product, and I will call this thing Y1 prime. Here we should have Y. So first one is a product of X and Y, and the second one is a product of Y and X. If these two things are products, then there is an in fact unique, as you were saying. Isomorphism from X cross Y to Y cross X. Making the following diagonal commute. So the thing is that I don't just want the two products to be isomorphic to each other. I want them to be isomorphic to each other in such a way that I know how to transition from projections of one to projections of the other. So this was the first product. The second product looks like this, right? But I can draw it swapped around. Just we'll keep the same symbols. So the pi1 prime was an arrow going from y plus x to y. So I can draw it here. And the other one is pi2 prime. And then I've got this thing in here. Let's call it I. And what this tells me is that not just that there exists some isomorphism between these two objects, which is what we were talking about all the time up to this point. We were just saying that there must be some kind of isomorphism. We didn't really care what properties that isomorphism has. But in this explicit example for sets, for instance, the isomorphism we had in mind is the one that swaps coordinates. And remember, in the category of sets, the projection maps will be choosing the coordinates, right? Pi1 will be choosing the first and the second coordinate. Now, the idea of swapping coordinates means that if I take a pair, swap its coordinates, and its second coordinate after the swap is the same as the first coordinate of the original pair. And that's exactly expressed by the fact that pi2 prime composed with composed with I must equal pi1. That's what it means for this triangle to commute. In other words, any two paths we take that start same spot and end same spot must be equivalent to each other in the sense of our earlier lectures. So the same must hold on this side. That will be telling us about the interaction of the second coordinate with the flipped pair. So let's write this equation separately. I composed with pi2 prime composed with I equals pi1, and pi1 prime composed with I equals pi2. Now, as soon as we write this down, we kind of immediately realize that, wait a second, of course there will be a unique morphism, not only just isomorphism, but a unique morphism making these two laws hold just by the fact that this is a product diagram. That's the definition of a product, right? If I've got a product like this, if I've got any two morphisms like that, there's always unique morphism here making equations like this hold. So this I as a morphism exists and is unique, having these two properties. So that part we actually already know from the fact that this is a product. What is new in this theorem is that this I will be an isomorphism. The uniqueness part is kind of something that comes from free, and the existence of the morphism I's comes from free. But the fact that it's an isomorphism is the thing we need to show. The proof of that. Okay, before I move on to the proof, everything is clear so far, Kokotisa?
Yes, it is. Yeah.
Okay, fantastic. So I know that I can find this I by the fact that the thing downstairs is a product, right? We agreed on that, right?
Yes.
But now we can apply the same idea the other way around. Let's use the fact that the top one is a product. And what do we get?
Oh yes, that we have another.
We get another one.
What is
That's
it?
right. Yeah, but it's called J.
Yes.
We don't know yet that they're inverses of each other. We can't just assume they are. But we will see how nicely we can prove that they will be. So far, all we know is that there is unique filler here, unique morphism here, making these two triangles commute, which just means another way of saying that these equalities solve. And similarly, there is unique morphisms here, making these commute as well. Okay. Now, what happens? So I want to prove, so required to prove, I want to prove that they're inverses of each other. I want to prove that J composed with I equals, okay, where are we now? I, J, right. So equals identity of X cross Y, right? Because J composed with I is doing I first, do I first, then do J. So it will bring us back to X cross Y. I want to prove that, and I also want to prove that I composed with J equals identity of Y cross X, in order for me to show that I is an isomorphism with inverse J, right? Okay. Now let's draw a separate diagram where we picture this thing. This time it will be connecting X plus Y with X plus Y. So I can draw a diagram like this. Of course, here then I will have the same pi 1, pi 2 above and also below. And I've got this J cross I. If only I knew that this composed with pi 1, J cross I composed with pi 1 equals pi 1, and this composed with pi 2 also equals pi 2. Let's say I know that, right? We don't know that yet, but let's say we know that. But then this will have to be equal to identity because, why? Because clearly the identity fulfills that, right? Clearly the identity composed with pi 1 is pi 1. Identity composed with pi 2 is pi 2, right?
Yeah, yeah.
So if I knew that this is also true, I will be getting two morphisms satisfying these equalities, but then by the definition of a product, there must be only one such, so they must be equal, right? So if only I knew that, then I could establish that they're equal, that these two are equal, just because this is already such, and there must be unique by definition of this product here, and therefore that other thing must be that as well. Can I get this? Well, it is actually not difficult to see that I can get this from these two commutative diagrams. And to see how we can get that, we will unpack this diagram and rewrite it in terms of the previous two diagrams, just by taking this diagram and kind of putting it under here. So this was our left-hand side diagram. The right-hand side one had a morphism J that now departs Y cross X, and it goes to X cross Y. Like this, right? Yeah?
Yeah.
So what I need to check is that this composite equals that, right? It's one thing I need to check. But on this diagram, it means checking that going this way is the same as going that way, right? Let me copy the picture here so it's more clear. You see, this part is the same as the top part. This is the same as the bottom part.
Okay, yeah, that's fine. So is it just brute computation and
Yeah.
hoping that some things simplify?
Yeah, yeah. But I wanted to show you a geometric version of that computation before we write it down algebraically. So imagine if we go back to the very first lecture, we were talking about train lines between towns and so on. So I've got this route here, right? I can think of the composite as a path of train lines, right? I've got this route. What I do know is that this is equivalent to that, right? That's the property of J. So the overall route here becomes equivalent to this one. But then that further is equivalent to this one. Yeah.
Oh, yes, yes.
Now algebraically we can write it down like this. Pi 1 composed with J composed with I equals, I swap the brackets, pi 1 composed with J, then composed with I. Pi 1J, which is this part, is pi 2 prime. So I've got pi 2 prime, then that is composed with pi, but that we already know is pi 1. So this equality here comes from there. and the other equality there comes from here. Does that make sense?
Yeah, that's fine. Yes.
In exactly the same way, we can establish the things on the other side. So let's establish. So we'll have pi2 composed with j composed with I equals. So I can regroup again with pi2 composed with j and then composed with I. Sorry, I think I misrepresented my picture, my colors here. So what I wanted to say, because the first one was just a rearrangement of brackets. What I wanted to say is that this equality corresponds to that one, because that's where we replaced pi1j with pi2 pi. This one with that, right? And then the
Okay,
other
that's
one,
fine.
yeah, then this one corresponds to that. The first equality doesn't have something on the picture, because on the picture these two are just the same path. It doesn't matter how we put brackets in a path because of associativity.
Yes.
Okay, so what is pi to j? This is pi to j is this, right? That's the same as pi1 prime. That's pi1 prime composed with I, and that of course is the same as pi2. Yeah. So in this case, this equality here corresponds to this commutativity there, is obtained from that, and then the other one is obtained from this commutativity here. Let me just move things around a little bit here, to fit it better on the picture. There we go. So we've established that, what did we establish? We established that this thing makes both this and the other triangle commute, but identity morphism also does, and so they must be equal.
Yes.
And that's how we prove the first of these. And guess what? The second one, well, it's just I and j. Change them around, right? It's exactly the same proof. Put the other diagrams, put the diagrams the other way around, on top of each other, right?
Okay, yeah.
And then that completes the proof. So we can now say that this proves that j composed with I equals identity x plus y. We can prove I composed with j equals 1 y cross x in exactly the same way, in a similar way. And then the proof is complete. Okay. So what have we proved? We have proved that if I have product of x cross y and a product of y cross x, I've proved they're isomorphic, but not only that, I've proved they're what we usually say canonically isomorphic. This isomorphic is not just arbitrary random isomorphism, it's the unique one that makes this diagram commute. And when your isomorphisms or in general morphisms are unique by a certain property of a diagram, by commutativity of certain diagram, we call such morphisms canonical morphisms. So one would say that product is commutative up to a canonical isomorphism. And by saying canonical, we also imply that it will be unique.
Okay.
Let's just add that remark. The commutativity of this diagram is the sense in which our isomorphism I is canonical. You see, in ordinary mathematics, when we're very used to having things equal to each other, we don't have to worry about canonicity of equality because equality is kind of unique already and already canonical. There's many options. But when equalities become replaced with isomorphisms, we could have potentially had some other weird isomorphisms between these two things that have nothing to do with those diagrams, and we don't necessarily want them. These non-canonical isomorphisms are not as well behaved as the canonical ones. So this is something that we often have back in our minds, that when I want to build an isomorphism between two things, I want it to be canonical in some sense, and not just some random isomorphism.
So the word canonical, does it have anything to do with universal, or those are two different ideas in category theory?
Canonical very often comes up also as a universal one. Wait, sorry. Okay. In this case, what is universal is the product. The product is a universal diagram of that shape.
Okay.
It's not the morphism it's not the morphism between the products that's universal. So canonical morphisms arise by universality of diagrams. But the canonical morphisms themselves are not the universal morphisms.
Okay,
that makes sense.
That makes sense.
Yeah. But there are also other situations when canonical morphisms arise not by universality of diagrams necessarily. We can also have some choice of diagrams that is not necessarily universal, and then canonical will be those morphisms that nicely fit in those diagrams. So the term canonical is used in contexts also where we don't necessarily have universality. We still want to use this term in such a way that we at least have uniqueness of some sort. It would be not nice to call something canonical if we don't know that there's only one such in a given setup. But anyhow, yeah. Okay, so we've kind of proved associativity, commutativity of plus or product, but then by dual argument we can get it for plus. And similar techniques can be used to show associativity. It will be a longer proof because it now involves three things, but it's achievable. And so this is the story of how some of the basic laws of arithmetic, in fact, do generalize. Not all of them, as we saw, but some of them do generalize for general categories. And that does mean that this unified concept of addition or multiplication that we've developed is not entirely useless. In fact, it's quite useful in the sense of not only identifying common patterns, but also of being able to prove general things about them that can be then applied back to the special cases to derive those laws without having to derive them separately, one for each special case. Now we know that product is always commutative up to isomorphism in every category. I know that this will be true for every special category as well. So if I'm studying some specific category and I'm working with products there, I don't have to reprove that they're commutative in that specific category anymore, because I know that it's true for a general category. So we're not only unifying concepts, we're also unifying theorems.
Yes, yeah. Again, very powerful, I think. But these are, of course, what are kind of well-established ideas within category theory, right?
Absolutely, yeah. We haven't done anything so far that's new. Even the approach to defining categories in the beginning of our lectures, although it was not a standard approach, it is actually kind of unpacking of a very important construction in category theory. So nothing that we've done is really new. We've studying really, really basics in this course.
Okay, that's fine.
All right, this brings us to the end of today's lecture. Thanks, Okotisa, for joining for the lecture. Hopefully others will also join us after the new year. That's when the next lecture will be. Happy New Year
Yeah.
to you and to everybody else who is listening to this before the New Year. And also Merry Christmas to everybody who is listening to this before the Christmas.
Yes, hopefully, what is it? New Year's resolutions will set in, but it's, I don't know.
Thank you.
That is fine.